question is posted on college board for the students to prepare for AP exam questions, and the question states, a group of students must determine the spring constant K of the spring that hangs vertically from a ring stand. The students attach a block to the bottom of the vertical spring as shown in figure 1, and figure 1 is right here. The students then put the block spring system 0.5 meters below the system's equilibrium position and release the system so that it oscillates. The students record the mass of the block and the period of oscillation T for several trials as shown in the table. For the part A, they ask you a question. The students want to determine the spring constant K of the spring. Indicate below which quantities could be graphed to determine the spring constant K of the spring by using the best fit line. You may use the remaining columns of the table as needed to record any quantities, including units, that are not already in the table. So let's see what we are having here. So we need to find K. So this is the one that we're looking for. And the students then pull the block spring the system 0.5 meters below equilibrium position and release the system in oscillations. Okay, so we will have our X is going to be for oscillations is 0.5. And the students record the mass. So the masses are every time different, so they vary, and the masses are shown in the graph in the table. So the students want to determine the spring constant. They don't stretch the spring and let it be in equilibrium, and then measure by how much it stretches, but they only place different masses and they determine the period. So I can use. So when they give you this type of a question, they usually looking for a linear relationship where the slope of the graph is going to be the value that you're looking. In this case, it's K. I'm going to write the formula for the period depending on the mass. So there's a formula. The period of this spring is equal to 2 pi and the square root of m over K. So I have to manipulate this formula to see how I can rewrite this formula, and then in terms of, I'm going to rewrite this formula in terms of y is equal to mx, and I don't have to say plus b because I don't have another constant here. So I'm going to do some work here. I'm going to square both sides of the equation. So I have t squared, 4 pi squared. If I square the square root, I have m over k. Then I can multiply both sides by k, so I have k t squared is equal to 4 pi squared m. And because my k is on the other side, and my k is going to be my slope, because I'm looking for that slope, so I could rewrite as m equals to k is my slope, and then I have t squared over 4 pi squared. Then this is my y. This becomes my y. This is my slope. K is your slope. And your x-axis is t squared over 4 pi squared. So what I need here is t squared over 4 pi squared. So I'm going to fill in these values, and then I'm going to start graphing. So I filled in my information. I've squared each period that was given and divided by 4 pi squared, and I got every single number. Now I'm going to use these numbers, and you can pause it, and if you do, and we're looking at the work on the paper, you can see that, and graph it in the graph that they give you below. And then also they ask you a question, indicate below which quantities could be. Okay, so the horizontal axis, I'm going to use, my x is going to be t squared over 4 pi squared, and my m is going to be my y. So I'm going to use the table that I just made for my t squared over 4 pi as my horizontal axis and m as my vertical axis, and try to graph the graph. And after I graph the graph, I'm going to find what my k is equal to. So I moved the table, the calculations, and the formula down here. And always when you do the graphs, make sure you label what your axes are. So my axis have vertical axis is m, and horizontal axis is t squared, and I have 4 pi squared. And then I also had to do my increments in certain position, and I looked at these would be the best, and that would be 1.2. So now I have for 0.3 on y, I have 0.15 on x, so it's somewhere here. For 0.6 on y, I have 0.03 on x. For 0.9 on y, I have 0.42 on x, somewhere here. And for 1.2 on y, I have 0.57 on x, so somewhere right here. So now if I place this graph, I have a graph, and my slope is k, because this is my x and this is my y. My slope is k. So if I want to find k, I have to do the rise over the run. So the rise goes from 0.3 to 1.9. So that is 0.9, or from 0.3 to 1.2. That is 0.9. And my run goes between 0.15 and 0.015 to 0.057. So that is 0.042. So my k is equal to 2143 newtons per meter. As the question continues, they use a different graph. They say figure 2, and this is what this question states. Another group of students performs a similar experiment in which the same block spring system from trial 1 oscillates, but in the horizontal direction as shown in figure 2. Frictional forces between the block and the surface are considered to be negligible. Furthermore, the student pulled the block spring system 0.8 meters from its system's equilibrium, so 0.8 meters from the system's equilibrium, before they release the system so that it oscillates. Will this change in the experiment affect the value of the period of oscillation, t, for the block spring system compared to the situation from part A? So I'm going to rewrite my equation for the period of oscillation. So the period of oscillation is equal to 2 pi m over k. So what changed is the position of it, and they said the friction is as negligible. So my period depends only on the mass, and it's the same mass, and k is the same spring. So because nothing changed in the formula, that means that the period of your oscillation does not depend on the changes that were made, and also it only depends on the mass and the k constant, and 2 pi is already a constant. So the answer would be a no. And for the last part, describe an experimental procedure to determine whether or not the period of oscillation t for the block spring system is different compared to the situation from part A. Indicate any steps necessary to include experimental uncertainty. Give enough detail so that another student could replicate the experiment as needed. Indicate a diagram of the experimental setup. Assume equipment usually found in a school physics laboratory is available. So for this part B, I would probably do exactly the same as what I did in the other setup number 1. I would use same masses. I would use the meter stick to pull out 0.8 meters distance for the 0.8 meter that they give you from the equilibrium every single time. So you have to use the meter stick. You have to try every single mass. You probably will have to use the stopwatch, because in the previous problem that's what you were measuring, right? You were measuring the mass. Mass was given in the time you measured. So in this case also, I need, for every single mass, I'm going to determine the time, so I need the stopwatch. And I will do a few experiments for each mass to see if it gives me similar times as in experiment 1, and I will compare those experiments. So it would look something like this. I would use the same setting as set up in 2. I will do multiple experiments with masses that are given in experiment 1. I will record my times. I may do a few experiments for each mass to see that it gives me approximately the same time as in the other problem. And then I will use meter stick, I'll use the stopwatch. And because they say include any steps necessary to reduce experimental uncertainty, the more experiments I do for each mass, the closer my numbers hopefully will be to the ones that I used to have in the first experiment. So that will reduce my errors. So the more you do the experiment for the second one to see how close the time is for each mass, that reduces your error in your experiment. And that's about it for this question.